Hello everybody. I'm back with a very simple exercise. I was actually hunting for a family of triangles, interscribed, that is to say inscribed in a first circle and circumscribing a second circle of the same radius. Okay, so if you take a first circle of radius big R, it turns out that if you come up with a copy of it, also radius r, but you separate their centers by this quantity, square root of 3r, this is going to subtend a family of Poncelet triangles, incident on the first circle and tangent, dynamically tangent to the second circle. So that's quite nice, right? So when you have a family of triangles, one thing you can immediately do is investigate the loci or the locus of some of its triangle centers. So right here I'm showing x1, the incenter, and we have this conjecture out that the locus of the incenter can only be a conic if the Ponceletian conic pair is confocal. Now obviously these are two circles. Two circles are only confocal if they're concentric. These are not concentric circles. So according to our conjecture from a few years ago, hopefully this curve cannot be a conic. It has to be of a higher degree. And I've already done some numerical evaluations of this, and it doesn't seem like this is a conic at all. It's a higher degree curve. Okay, let's look at the barycenter. So the barycenter, there's a second theorem out there I believe by Schwartz and Tabashnikov that say that for any pair of Poncelet conics, the locus of the barycenter is a conic. Okay, so here it looks like this is going to be a conic. We'll have to investigate that, but let me go ahead and postpone that, or leave that as an exercise. Is this a circle? This could be, let's check. Okay, is this any close to being a circle? Let's go ahead and say, okay, I want to do a circle through 3 points. I'm just going to choose 3 points on the locus. Yeah, so it looks like the locus of x2 is a circle of the same radius as the two circles that form the Ponceletian family. So that's a conjecture. You would have to be checked, okay? All I've done here is completed the locus by selecting 3 points on it and asking GeoGebra to draw the circle that goes with these 3 points. I'm just eyeballing this too, and it looks like it's also a circle of the same radius as the first two. So that's a cool result in itself. Okay, so let's go ahead and continue our investigation. Now, the circumcenter obviously is going to just be the center of the fixed circumcircle of the family. So x3 doesn't move across the family, right? Let's keep going. How about x4? Now x4 has a nice shape as well. This could be a conic, likely going to be a conic. But I want to get to some cooler results that happen at the higher k's here, okay? So, let's just take a look first of all very quickly at these loci, because some of them are beautiful. We're going to hit upon a couple of degenerate ones. So here's x5, here's x6. It would be cool to investigate if this is a parabola, for example, okay? x7, and I'm going to leave a link in the description to this experiment if you guys want to play with it on your own time. x8 has this really interesting shape, right? Where it seems to be tangent. It looks like a strophoid of sorts, but it's not a strophoid. But it looks like it's tangent to the second circle at the intersections. It has this interesting loop, and this almost looks like a focus of the loop in some strophoidal sense. So we'd have to investigate what's the order of this curve and if this curve is cataloged. Okay. x9 looks like a circle, but that would surprise me. Let's see if this thing is a circle or not. I'm going to put 3 points on it. 1, x9 itself, and no, you can tell it's not fitting. You can see that there's an error there, so this is not going to be a circle. Okay. Yeah, so let me remove this tentative circle here. x9 tends not to be very well behaved. Okay, it's very seldom it is a conic or things of that sort. x10 is looking a little distorted here, asymmetric, so this has no chance of just being a pure ellipse. x11 has this really cool shape as well, the Feuerbach point. Feuerbach point is sweeping something that looks like, again, a strophoid, but it's not. It's trophoidal, right? It's a trophoidal curve. And the endpoints of a lot of these loci are the top and bottom poles of one of the circles. I'm using the term pole here, but this is immaterial. I mean, if you drew a line that is perpendicular to this axis here, you would intersect the circle up here and down here. Okay, so the reason this is happening is because at this limit point, the triangle degenerates, and you get the sort of top tangent here, and the triangle turns into a line. So you can no longer talk about loci. In fact, if you continue the point over here, you just retrace the curve in the opposite direction. Okay? All right, so this is x11, kind of good looking. x12, x13, x14, x15, x16 is some external thing. You can see here, right? Some external thing. Let's go back to where I was before. I believe it was here. No, one more. Yeah, that's it. Let me just put this, let me just center this so you guys can see it on the video. Correct? Yeah, let's go to x16 if I can. So 17, 18, strophoidal-like, but of no particular interest. 19, 20 is probably going to be a low order, low degree curve, something like a conic. Okay, so we have to investigate. On a previous video, x20 seemed to be describing a straight line, but it was a family of triangles between two rotated ellipses, identical and rotated golden ellipses. So take a look at the previous video. I'll leave a link in the description. So here's x20. Now, as you go through these, okay, many look like parabolas. Oh, this is a first interesting thing. So x25, which is a point I don't think we've ever studied in the past in any specific way, seems to be a straight line. Would have to open up ETC, the Encyclopedia of Triangle Centers, and study what this point is about. And why is it that for this family of triangles between two identical circles, this thing becomes a straight line? I try to do this with a generic excircle of some generic triangle, and x25 is not a straight line. It's only a straight line if you're taking this particular configuration here. It's a particular triangle with a particular excircle. So you have this isosceles here. Okay, so we have to figure out, let's go ahead and get a reading on that angle there. So I can say angle. I'm just gonna say 1, 2, it's gonna tell me, oh, not in that direction, give me on the other direction, please. Not like that. Let's go ahead and do in this direction. Yeah, so GeoGebra is telling me that, let me see if this thing is centered, yes it is, that angle is about 42.43 degrees if you want. I mean, I'm probably not exactly symmetric here, but it's something in that 42 to 43 degrees. So if you take this triangle, and it would be nice for us to understand what the specific angle of a isosceles triangle, the upper angle, is, so that the bottom excircle has the same radius as the circumcircle. So this is the first exercise. What is this triangle? What are the sides of this triangle? What are the sides of an isosceles triangle such that the lower, or sort of the bottom excircle has the same radius as its circumcircle? Okay, so that's sort of the point of departure. This is how I started, but I never did anything algebraically. So we're getting a 43-degree angle here at the at the symmetric location, at the isosceles location. And what is this angle? Is the cosine or tangent of this angle a rational number? That would be a cool thing to do, right? And then the other question is, why is it that x25 seems to be sweeping a straight line? Quite curious, right? Okay, let's keep going. So I'm just going to skip around here because I want to get to another very cool result. Well, also I want to appreciate some of the results here. Here's x36. Okay, now we have a paper out. It's on archive right now, and it's about to be accepted for publication, where we make the following statement. For a family of Poncelet triangles inscribed in their circumcircle, okay, and circumscribing a circle. Now in our paper we only consider the incircle, but here we're considering an external circle, so this is like an excircle, right? So our claim is that x36 okay, is always going to be a circle. And we're verifying that here, even for the case of the excircle. So it looks like x36 is tracing, okay, up to that meeting point there, an arc of a circle. Okay, so this actually shows that our theory was mostly focused on the incircle. So a triangle family, or a family of Poncelet triangles inscribed in a circle and circumscribing their incircle. We got a bunch of results, and it looks like these results preserve their algebraic structure if you, instead of the incircle, you consider an excircle as the caustic for the family. Okay, so x36 is a circle. Okay, let's keep going. So let me go ahead and make this big again. Okay, so 37 is the strange curve, 38, 39. 40 is also a, I think this is the Bevan center. It tends to be a particular triangle center that has sometimes nice properties. So it could be that x40 here is sweeping a conic, for example, even a circle. This doesn't look like a circle, but perhaps a conic. One way to do this with GeoGebra is I can place 5 points on the locus. So 1, 2, let's put 1 over here, and then 4, and then 5. Yeah, so let's look at this guy here. So here's how I do it with GeoGebra, right? First of all, I eyeball it. This is kind of looking circular, right? It's looking circular and concentric with a caustic, which would be a cool thing. So it looks like, yeah, let's look at that radius there, because I can inquire. Yeah, so for example, the first thing I can do is I can say focus P. Yeah, so it's placing the two foci over here. This could be a numeric instability, okay, thing. But there is a good chance that this thing is a circle, okay, and it's concentric with a caustic, okay? So let's forget about that for now. Yeah, so, yeah, let me remove this thing from here and clear everything. Okay, so this is 40, 41, 42, 43. 44 has this interesting Pascal-like, not really, right, but this pear shape, okay, very interesting. This triangle center tends to produce some really nice loci. Anyway, let's continue. 45, 6, 7, 8. So 49 is also interesting, right? It's sweeping a line. And the line goes through infinity, right? So it's going through infinity on the right, and it comes back through the left, and then it reaches an extremum right here, and then you repeat the same thing. And the extremum on the other side is the center of the caustic triangle. So why is 49 doing that? Kind of curious. All right, here's 50. I don't know what 50 is. This is looking like perhaps a parabola of some kind, right? So we'd have to investigate that. I want to get to cooler results or more beautiful loci. Let's look at, yeah, 59 typically gives us very interesting curves, right? High order curves. There's a case, and we show this on our paper, where x59 collapses to an ellipse. Okay, but typically it's a multi curvature minima extrema curve. Okay, so it's a high order curve. All right, let's keep going. 60, 64 sometimes has, you know, low order manifestations. 65, 67 looks interesting as well. Like this looks like a limaçon of sorts. Well, let's ignore it. 68 looks interesting as well. It's just kind of like an arc, perhaps. It's not going anywhere beyond this arc. This salt and pepper noise here has to do with the locus plotting going unstable when you go through this eversion here. Okay, let's go to 69, 70. 74 is a point which is always on the circumcircle, so it's just sweeping Okay, an arc of a circle here. Okay, nothing really interesting. Yeah, here's 76. 76 is reminding me of x8. Perhaps they're the same. I go back to x8. Right, remember x8? Yeah, so this is x8, and now if I fast forward to 76, you got something similar, right? Okay, 7, 8, 9, 80. Interesting. Let's just skip these guys because there's one coming up which was fascinating. Well, 88 is kind of a beautiful locus, right? Look at that. It's looping around itself, and then it ends up at this northern pole, and then it loops around itself, and it ends up symmetrically at the southern pole. And along with 44, 88 is a creative kind of triangle center. 89, looking quite symmetric, perhaps circular. 90 seems to be, and this is kind of strange. Wow, I had not noticed this on my first battery of tests. Let me get rid of this angle because we don't need it anymore. Why is it that x90 is the vertex? Right, it's just stuck on the vertex. Very interesting. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8 is always on the circumcircle, so it's just sweeping, just doing a complete sweep of the circumcircle. Nothing too interesting, and we're going to get the same phenomenon for the next 2 or 3 triangle centers. So 99, the Steiner point, is always on the circumcircle, and it's sweeping it at, looks like at twice the speed, right? Or maybe 3 times the speed. Let's go to 100, right there. Is it 9? No, 90 and 100 are not on the same spot. Okay, and then I think 101 is also on the circumcircle. 102 is in the circumcircle as well, and I think 103 is on the circumcircle. Yes. Now I want to get to the next interesting thing, which I think is 155, and then we'll stop. Okay, so let's just keep going. A lot of these points are on the circumcircle. X110 sometimes has interesting results. You can see here that I think this is the focus of the Keeper parabola. You can see that its extremum is the intersection between the circles, and it's always on the circumcircle, right? So its extremum is right there. Okay, cool. Let's keep going. X11, 12, 13, 14. I want to get to 55, okay? But let's just see if there's anything interesting. Here's a strophoid-like locus. 117, doing some wild swerving. Kind of cool, right? Okay, let's go to 118. Oh, 119 is basically just pinching at the intersection. 120 is this sort of cochleoid-like curve that ends there. Okay. Now these triangle centers, although they have some properties, their actual design is arbitrary, right? So this is the result of humans coming up with algebraic expressions that have a certain symmetry required by triangle centers. But you know, the number of triangle centers is obviously infinite, and the number of algebraic formulas is also infinite. Probably one is countable and the other is not. But let's keep going. 121. So here's another cochleoid-like curve. Okay. 3, 4, 5, 6, 7, 8, 9 is doing something strange. Let's see how strange this is. Is this thing just like not around at all? Yeah, some points are not around, or they cannot be properly plotted. This is looking to me like a cochleoid that GeoGebra is not being able to plot. You can see this, right? It's going unstable. One way to see this is just by adding a trace, and then I'll do the locus manually, like that. Yeah, so it's this kind of ugly thing. Okay, no particular interest. Okay, let me go ahead and get rid of it. Let's get rid of the trace. Now let's go to 130. Okay, 131, 132, 133, 134. One other Yeah, 136 is doing something interesting as well. Look, it's only going through that arc of the excircle of the caustic. Wow. Interesting, right? It's locating itself on that arc. All right. 7, 8. Oh, look at how beautiful. You know, when you start going up, you start getting these higher order triangle centers and you get more ornate loci. Look at that. Self-intersecting, multiple extrema of curvature. So this is a high order, high degree curve. Let's keep going. I'm getting to, my goal is 155, 139, 140 and 141, they tend to be simple. Let's look at 141. Yeah, so sometimes because they have certain properties, they are fixed linear combinations of x2 and x3, I believe. At least 141 is, I don't think 140 is. This one is not, but this one is. So sometimes you got some degree collapse on the loci they sweep, but this doesn't look so interesting. Let's keep going. 3, 4. Look at this one. This one is kind of an interesting, highly nonlinear curve, right? Like a deltoid kind of thing. Okay, 144. 5, 6. 6 is looking circular, but let's ignore it. 7 is looking like, you know, some Lissajous, not Lissajous, but Limaçon shape. Okay, let's keep going. We're almost there. 8, self-intersecting. 9, 50. 1, 2, 3, 4, 5. Okay, so we're going to end on this note. Why is 155 stationary on the other center? What is going on here? Can somebody study this for me and tell me why this 155 point is stationary? How cool is that, right? What is 155? Let me go ahead and do a short lookup here. I'm going to go into... What I typically do is I look for these properties here. For example, over here, to see if any one of these properties, okay, implies, and let's go back to x25, so you guys remember what I was doing. You will remember that x25 had this property. So what is it about the geometry of x25 that is making its locus collapse to a segment? Okay, and what is it about 155, which we're going to be looking at shortly on ETC? So here's 155. Why is it that 155 is stationary? Let's look at what that is. So I'll go back here to x155. Eigencenter of orthic triangle. Okay, so that's not very helpful. But what you need to do is you actually need to read this very carefully and see if there's any properties down here, okay, on ETC for 155, that would basically say, look, this has to be the case that over this family, you know, this triangle center is stationary, right? The fact that it is stationary, I thought that was kind of cool. I didn't see anything beyond that. Let's just very quickly go all the way to, let's go all the way to 200. To see if there's anything that sort of jumps off the page. Doesn't look like it so far. Yeah, here's another strophoid-like beast. 184 is interesting because it's actually, now it's the semi-infinite line, right? It doesn't come back to the other side. Okay, 184. I'm just going to stop at 200. 185 seems to be also sweeping now a segment, just a segment. Okay. Okay, 186 is sweeping a same radius circle. That's pretty cool. Remember x40 was sweeping a similar circle, although x40 was, I think it was twice the radius and it was concentric with a caustic. Okay, so this one is just sweeping a same radius circle. 7. You got this nice tangency here. 8, 9. Oh, look at this guy here. It's like it self intersects in a very interesting way. Yeah. Okay. Kind of cool. All right. How about 200, 190, 191, 92, 93, 94, 95, 96, 97, 99, 200. Okay, so I'll just leave it at that. Don't remember the Alamo, remember X45. Was it 45? No, I think it was 25. Remember X25 and remember X155. How about that? Stationary. See you on the next video. Thank you.